So in this video, we're going to look at some examples of calculating or finding, indefinite integrals when we're working with polynomials. So we're going to have three examples. Here's the simplest possible case. So step one, rewrite the indefinite integral in your own handwriting. Step two, in this case, what I want to recognize is that if I just have the antiderivative of dx, or the integral of dx, I want to recognize that this is really a 1 dx sitting here. So if we're integrating 1 dx, remember we're looking for an antiderivative. We're looking for an antiderivative of 1. So what is the function for which the derivative is 1? And what we need to recognize is that if we have just an x by itself, the derivative dx of x is just equal to 1. The coefficient on the x term is the derivative. So x is an antiderivative of 1 with respect to x, and then we have to add on plus our constant of integration. And of course your check on your work would be to take the derivative of that, take the derivative d dx of x plus c, and make sure you get back a 1. So the original function in there is f of x equals 1. We have calculated an antiderivative, big F of x. Our claim is that the antiderivative is x plus c. So to check your work, you want to calculate what's the derivative of the function that you found. And the derivative of x is 1, plus the derivative of any constant is 0. So we just get our 1 back. So the work checks. So here I have a linear function sitting in here. So my function little f of x is x plus 2. And we are being asked to integrate that. So I'm going to rewrite the integral. And then from the previous video, what we want to recognize is that if we have a sum or difference of two functions, that we can break it up into individual integrals, just in the same way that we could break up sums or differences of functions when we were differentiating. So we can break this up into two integrals. And the antiderivative of x, we will rewrite one more line, x dx plus, this is a constant times dx, so I want to recognize that the constant can be factored out. So just like in the previous example, I really have a 1 dx sitting here. And then the antiderivative of x, or an antiderivative of x, we're going to make the guess. This is x to the first, so we're going to guess that the exponent is 1 larger. And then we're going to say, hey, if I took the derivative of x squared, what would that give me? Well, the 2 would come down in front. So we're going to need a 1/2 to kill the exponent 2 when you take a derivative, when you check your work. So if we take just dx of 1/2 x squared, we get 1/2 times the exponent 2 comes down times x, we get just a single x sitting there. So plus, I have a constant times the antiderivative of 1 dx, and we know that the antiderivative of 1 is just x, and then we're going to get plus a constant of integration. So one thing to recognize is really with each integration you get a constant of differentiation. So I'm really getting plus a first constant of differentiation plus 2 times what's the antiderivative of 1 dx, what's an antiderivative of 1 dx? Well, an antiderivative is x, and we get plus a second constant of integration. So each integral generates its own constant of integration, but then you can add two constants together. So constant 1 plus constant 2, we can just say that's a third constant, we'll call it c. So c sub 1 plus c sub 2, let that equal c. So we just get 1/2 x squared plus 2x plus a single constant that came out of adding the two constants together. So usually when you are integrating, you're not expected to show each constant happening. You're typically going to be allowed to add them together in your head and recognize that you have generated a single constant when you add the two constants together. So pretty traditional not to show them like this, but to just go straight to the plus c form. Again, the check on work, if you wanted to do it, would be to differentiate the result and make sure you get the x plus 2 back, the function that's inside the integral notation. So if we did that, we would be taking d dx of, if we wanted to check our work, 1/2 x squared plus 2x plus c. And we know that we're able to differentiate them individually, so we would get 1/2 times 2x from there, plus the derivative of 2x is 2, plus the derivative of a constant is 0. A half of 2 is 1, so we get 1x plus 2 plus 0 is just 2. And there's the original function back. There's integration and differentiation acting as inverse operations in some sense. So the last example, I've got a 4th degree polynomial sitting here. So step 1, rewrite the equation in your own handwriting. Integrate, parentheses, the parentheses is required if you write it without the parentheses. So for example, if I write 3x to the 4th minus 5x squared plus x dx, then the integration symbol is only applying to the 3x to the 4th, and x is being multiplied by dx, but nothing else is. So I need the parentheses around the function that's being integrated, and our function little f of x that's being integrated is the function 3x to the 4th minus 5x squared plus x. And then what I'm going to do is recognize I have a sum or difference of terms, so I can break it into individual pieces. So integrate 3x to the 4th dx minus integrate the 5x squared dx plus integrate the x times dx. And then we could even rewrite this again, because I have a constant times a function. I have a constant multiple of x to the 4th, so the constant can be factored out. 3 times x to the 4th dx minus a constant multiple times x squared, so the constant multiple can be factored out. So x squared dx left inside plus the antiderivative of x dx. Now, each of these integrations generates its own constant of integration, c sub 1, c sub 2, and c sub 3, but we're going to add those three constants together to make a single constant that we'll call c. So integrating again is kind of a matter of guessing a little bit. This is x to the 4th. So we need the function whose derivative is x to the 4th. So my guess would be an exponent 1 larger. But if I differentiate x to the 5th, the 5 would come down in front, and I don't have a 5 in front right here. So we're going to multiply by a 5th, which would kill the 5 when the exponent came down upon differentiation. Minus 5 times the antiderivative of x squared. Guess that the exponent's 1 larger. So the derivative of x cubed would be 3x squared, which would give us the x squared, but that would put a 3 in front, so we're going to multiply by 1/3 to kill the 3, plus integrate x. This is really x to the 1st, so we're going to increase the exponent by 1, and then recognize when we take the derivative of x squared, you get 2 times x, so we need a 1/2 to kill the 2 when it comes down. And integrating each of these generates 3 different constants of integration, which can be added together and represented with a single constant. And then we can kind of simplify things a little bit. 3 times a 5th is just 3/5 x to the 5th, minus 5 times a 3rd is 5/3 x cubed, plus a 1/2 of an x squared, plus a constant of integration. And again, if you wanted to check your work, you would differentiate this and make sure you get back the original polynomial. So our work check would be to go, what's d dx of 3/5 x to the 5th minus 5/3 x cubed plus 1/2 x squared plus c. So if we differentiate this one, we'll get 3/5 times, bring the 5 down, decrease the exponent by 1, minus 5/3. Differentiate x cubed means bring the 3 down and decrease the exponent by 1, plus 1/2, times differentiate x squared, bring the exponent down, decrease the exponent on the variable by 1, and then the derivative of a constant is 0. And here we get 5 divided by 5 is 1, so we get 3 times 1 is 3x to the 4th, minus 3 divided by 3 is 1. 5 times 1 is 5. X squared plus 1/2 of 2 is 1x. And then the plus 0, we don't need to write that. And then you look back up here and say, did that indeed generate the original polynomial, which it did? So we're confident that our result here is correct.